Okay, again, welcome in the lecture Facts and Power Quality. We were discussing about the static series compensator. In the static series compensator, in the last lecture, just we'll take the review. It has been discussed the concept of series compensator, the need of the series compensator. It is found that as the EHV transmission line, AC EHV transmission line, the length of the transmission line increases. At the same time, the power handling capacity at particular voltage, it decreases. So which is quite clear from this table. The power handling capacity or steady state stability is limited with the reactance, transmission line reactance, which is given by the power is equal to E1, E2, this equation, power is equal to E1, E2 upon L into X, where L is the length of the transmission line in kilometer, and X is the reactance per kilometer, sine delta. For 30-degree, delta is equal to 30 degree. We found that the power handling capacity, say, for example, 400 kV transmission line, for 400 kilometer, 670 megawatt can be transmitted with the transmission line. But for the 600 and 800 kilometer, the power handling capacity get decreased. Because of this, it is restricted due to the reactance of the transmission line. So the series compensator, the objective of series compensator is to decrease this denominator by using some series capacitor, and definitely when the denominator L into X get decreases, the power handling capacity of the existing transmission line of same voltage level get increased. So this is the some objective which we have already discussed, and this is the basic concept of series compensator. We have connected a capacitor in a series with the transmission reactance, and because of this transmission reactance, the effective value of reactance will be X minus XC, where X is the reactance of the transmission line and XC is the capacitor connected in series with the transmission line. And it is found that this is the without any compensation, series compensation, when K is equal to 0, K is nothing but the degree of compensation, which is the ratio of XC upon reactance of the transmission line. So when K is equal to 0, the compensation degree, the series compensation degree is equal to 0. This is the power angle characteristic, whereas the value of K get increased, say 0.2 and 0.4, the power handling capacity of existing transmission line get increased. This is the concept we have seen in the last lecture. Now, today we'll see the voltage stability by static series compensator. This is the same which is we have already covered in the shunt compensation. This is for the radial line. This is comprises of source voltage or the transmitting from it. It is going to transmit from this one. And this is the reactance of the transmission line, existing reactance of the transmission line, where this is the controllable capacitor is connected in series with the transmission line. This is load impedance and low terminal voltage. In case of the shunt compensation, we have used such type of circuit. This is the capacitor, this is the reactance of the transmission line. It's quite same. This is the sending end voltage. This will be the without any compensator. This is the load ZL. And it is found that because of without any compensation, I am discussing for the shunt compensation. Okay, first then the same we will going to discuss with the series compensation. So this is the power P and this is the voltage. Definitely it is in the percentage voltage and percentage power. And it is found that for uncompensated line, it is depend upon the power factor. And as the power factor decreases, say the voltage stability also get decreases. Say it is say 0.8 power factor, it is 0.9 power factor. And whereas for the leading power factor, the voltage profile is not constant and it is get increased because of the unity or leading power factor. Whereas as soon as we connect some compensator over this one, so because of this compensator which we have connected near to the load for the radial transmission line, instead of this one, it is quite flat, or the voltage profile get improved, and voltage profile may be like that. This is the percentage power and same thing. So we will get such type of curve. Such type of curve for the different power factor. So it is found that because of the shunt compensation which is connected near to the load, the requirement of the reactive power is going to fulfill by the compensator. The compensator which is connected near to this one, it is going to supply the leading kVAR or MVAR required by the load, and hence the requirement of the reactive power from the source get decreases, because this transmission line, this source is going to supply, say it is kVA, which is equal to kilowatt active power plus j kVAR is the reactive power, or it is maybe written in the MVA also. The same, the amount of reactive power that is going to supply from the source is get reduced, and hence the voltage profile of the radial transmission line get improved. Now same thing over this one. In this condition, the series capacitive compensation can also use to reduce the series reactive impedance to minimize the receiving end voltage variation and possibility possibility of the voltage collapse. So what is the difference over this one? It is going to supply the reactive power needed by the load, whereas when we are connecting a capacitor in series with the transmission line, total reactance of the transmission line get reduces by some factor. It may be a 30%, it may be a 20% or 50% as required. So there is a two different method, but the effect is same. Here the reactive power is going to supply by the shunt compensation. Here the series compensation is going to minimize the series reactive impedance. This is that important. It is going to reduce the series series reactive impedance to minimize the receiving end voltage variation. So here, if you just see the figure, the same variation we have, same relation we are going to discuss. This is the voltage in PU in percentage, or it is in PU, whereas power also in the PU. So for without any series compensation, when K is equal to 0, when K is equal to 0, what is the value of K? K is nothing but it is the ratio of K is equal to, it is the ratio of capacitive reactor or connected in series divided by the normal value of the transmission line reactance. So when this K is equal to 0, this XC is equal to 0, K is equal to 0. So without any compensation, this is, say, it is going to supply near to the 1 PU, or it is for the rated power. It is going to supply the rated power, but at this rated power, the voltage collapse occur very early, isn't it? Now, when the K is equal to, when the K is equal to 0.5, it means that XC is equal to, say it is equal to, XC is equal to 0.5 K, 0.5 X. So at K is equal to 0.5, it is find that the capacitive reactance which is connected, it is the 50% of its capacity of the transmission line reactance capacity is connected over this one. So the power get increased, and which increase the voltage stability. Similarly, when the X is equal to 0.75, means 75% of the transmission line. So again, the power handling capacity get increases with respect to the, the voltage get increases, the voltage collapse get increases, and it increase this one. So here, by using the series compensator, one may increase the voltage stability of the transmission line. Second, very important, it is the improvement of the transient stability. In the Shunt compensation, it was discussed that this is the P delta curve. This is the P delta curve for the normal transmission line. Say this is the reactance, and two machine system is there. We are considering two machine system. This is the transmission line reactance X. This is the voltage, say V1, and this is V2. But the voltage V1 is equal to V2 is equal to V for our simplicity. So power is equal to V1 V2 upon X into sine delta. This equation we have considered many times. Now P is equal to, as V1 and V2, the magnitude is same, so it is V square upon X into sine delta. So this is the power. P is equal to V square upon X into sine delta. So this one, and it is give the sinusoidal waveform where maximum power is equal to. So here the P maximum is equal to sine delta is equal to 1. So it is V square upon X. So it is V square upon X. So this is the condition before any fault. The mechanical input and electrical output is same for the two machine system or whatever this one, or under such condition, it is working over this one at delta is equal to 0. Now, as soon as the fault occur near to the generating station or sending station, the power P of this generator or this from this end, P is goes to the 0 value. The power becomes 0, and here the point comes to the 0 power. This is the power is equal to 0. So it becomes 0, and it will remain 0 till opening of the circuit breaker. Let the circuit breaker open over here. So this area is the acceleration area, because the output power is equal to 0, whereas the mechanical input will remain same. So the generator will accelerate. And area A1 is equal to, this is area, what is from delta 1 to delta 2, from delta 1 to delta 2. The maximum power is Pm here for this working point, Pm minus 0 d delta. So this is the A1. Now, as soon as the fault clear, the circuit breaker open, the generator will decelerate and it will oscillate. The angle is going to oscillate. The maximum oscillation is from up to this point. So this is the maximum oscillation. At this point, the area A1 and area A2 become equal and the system will be stable. So this is the two machine system, and the fault occur near to the load, near to the say generating station itself. So therefore the A1 and A2, and when A1 is equal to A2, the system is stable. This is the, now under such condition, what is that? If the area A2 become equal at delta 3, this is the margin. This is the margin which says that this much is the transient stability margin is there. If the fault clear over here, definitely the area is going to increase in this side. So again, the margin is decreases. If again the fault cleared over here, so it is utilized entire area, and we can say that there is no margin for the transient stability limit. So we want, our objective is to increase this area, marginal area. If we are able to increase this marginal area, it means we are going to improve the transient stability with the help of series compensation. Now, a series compensator is connected. When we connect the series compensation, say this is the capacitor which is connected in series with the transmission line, and rest of the system is as it is. Say two machine systems are there. This is the value of XC, this is the XX, and voltage V1, V2 at its is this one value. So what is the value of K? Where K is equal to XC upon X. Okay. So the power P is equal to this equation. This is the power V square upon X 1 minus K into sine delta, which we have already derived in the concept of series compensation. So this is the older without any compensation. This is the marginal area. Whereas if you connect a capacitor the new curve will be this one, because P is equal to V square X1 minus K, say K is equal to 0.3. So it is 0.7. So as per the earlier case, P is equal to V square upon X into sine delta. This is the this equation. This is the curve. Okay. Now this equation, if 1 minus K, where K is equal to 0.3, then we can write as it is equal to V square upon 0.7x as it is into sine delta. So definitely this power PS, we are going to indicate as a series compensation power. After series compensation, the power PS is equal to V square upon 0.7x. Definitely it is greater than this curve. So this is the curve. Now under same condition, this is the delta 1 as discussed in the without any compensating line, at which the circuit breaker open. So area A1 or area AS1, ASS is suffix only for representing this is the series compensation after series compensation. So this area A1 is similar to or the same equal to in magnitude equal to the previous case. So see here, it is the area A1 and area AS1 is as it is. Whereas AS2 also become equal. When AS1 and AS2 become equal, the system will be stable. AS1 is equal to AS2, the system becomes stable. But what is the difference in the previous case? The difference is that here the marginal area or the area margin is very large as compared to the without series compensation, and hence one may say that with the help of series compensation, the transient stability improves. Okay. So even though if you are working at higher voltage, the system will remain stable for the new value, isn't it? Even though if it is getting increases from delta 3, may from here it is delta 3, new delta 3 is DS3 is there. Even that we found a sufficient margin in the deceleration area. Therefore, we can say that with the help of series compensation, the transient stability can be improved very well. Now, third point is the power oscillation damping. The same thing discussed in the shunt compensation. Whenever the fault occur, whenever some large disturbance occur, after large disturbance, the angle delta is going to oscillate. And if the oscillation remain for a long time, the system may come out from the synchronism or may come out from this one. Say, for example, for the modern and large capacity generating station, after few oscillation, this angle get increases and hence the system become unstable. Okay, so our interest is to decrease this oscillation or damp out this oscillation. Because of this undamped system, because of oscillation in the angle, the power get oscillate. So it is necessary to mitigate this oscillation. So similar to the shunt compensation, if you pump the reactive power in such a way that it mitigates the oscillation, definitely the oscillation in the power or tie line power can decreases. So when the rotational oscillation generator accelerate, the angle delta get increase, and therefore as the delta angle increases, this angle delta, so d delta upon dt is more than 0 value, and we can say that it increase, we have to increase the compensation. And similarly for the opposite one. So these are the some points, these are the some say application of the series compensation. Very first, it improved the power handling capacity. First point, which is very much important, one is the to increase the power handling capacity. Second, voltage stability. Third, transient stability, and damp out the oscillations in the angle as well as power. Now, In the shunt compensation, we have seen there's a controllable VAR generation. We want the control over the generation of the reactive power, inductive reactive power or capacitive reactive power. When it is inductor is connected, it consumes or it absorbs the reactive power, whereas when capacitor is connected in parallel or in shunt, then it generate the reactive power. Similarly, in the series compensation, the control over the compensation is going to obtain with the help of thyristor switch capacitor and thyristor controlled reactor to realize the variable reactive admittance. Our objective is to introduce the reactive admittance. Either it is a capacitive admittance or inductive admittance. So the control over this admittance is done, may be carried out by the thyristor switch as well as switching converter. So switching converter types also get realized or is also possible in the controlling the capacitor. Second point, the series compensator is a reciprocal of shunt compensation. Shunt compensation, we are providing the reactive power, whereas we are reducing the reactance of the transmission line. So it may be called as a line length compensation. So the shunt compensator is functionally a controlled reactive current. It is going to control the reactive current source, which is connected in parallel with the transmission line to control its voltage. So what is the main difference? Say this is the transmission line. Okay. This diagram we have considered in the very first unit. This is the shunt compensation. This is the shunt compensation, and it is going to inject the current at the point of connection, or it absorbs the current when it is a reactor. Whereas for the series compensator, a series compensator is functionally a controlled voltage source which is connected in series with the transmission line to control its current. So the difference between this one, so here this is the series compensation or compensator. It may be a fact device, and here it is going to inject the voltage, and here it is going to inject the current in series with the transmission. So this is the difference. And next point, the operation of shunt compensator is viewed from the perspective of the transmission voltage and that of the series compensator from perspective of the line current. So this is the 2 points, the differences between the shunt compensation and series compensation. So in the next lecture, we will see the controllable series compensation, the procedure, how to control the series compensator in the transmission line. Thank you.